This worksheet is going to give you a chance to practice drawing some fatty acids from not from their names, but from a description of their structure. And we're going to draw 3 different types of fatty acids. The first one that we're drawing is Cysts, Palmitoleic acid. And it tells us that it's a 16 carbon mono unsaturated. So that means it has 1 carbon-carbon double bond. And it tells us that the double bond is located at carbon number 9, and we need it to be in the cis configuration, so that's coming from the name. So let's just start by making a note of the shape of cis versus trans. So our cis molecule has got, if we're looking at the double bond, it's got the same, 2 of the same things on the same side of the double bond, and our trans has a shape like that, where when we're looking at the double bond, we have 2 of the same things that are on opposite sides of the double bond. So we have to remember that. The other thing we have to pay attention to, and this is something that's very confusing to a lot of people, the location of the double bond, which is carbon number 9. And that is not saying that the double bond is omega 9. So those are 2 different types of notations, and you have to be on the lookout for specifically, unless they specifically say omega 9, then you're going to assume carbon number 9 counting like you would normally count from the carbon-oxygen double bond. That guy is going to be carbon number 1. That's a really funny looking 1 that I just drew. So you've got to be really versatile with that, and you've got to pay attention. If they're saying omega, then you count from the end, and if they don't say omega, never ever assume they mean omega. They do not mean it if they don't say it. So we're going to draw 16 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that 16th carbon that I drew is the one that I'm going to make into my carboxylic acid group. And now I'm going to go ahead and number those carbons like we would normally number. So we're starting with the carbon-oxygen double bond, and we're numbering away from the carbon-oxygen double bond. And I really don't need to put all of the numbers in here, but I'm putting them all in there just so that we can be sure that we have all 16 carbons. So excuse me, I haven't had to sneeze. So we've got all of our carbons in place. Now we need to put the double bond in, and the double bond is located at carbon number 9. It's been a while since we talked about alkenes, but located at carbon number 9 means that the double bond starts at 9 and goes to 10. So there's the position of our double bond right there. Now, unfortunately, what we have drawn is trans. That is not the cis configuration of this molecule. So what we are going to need to do is erase and fix to make this into a cis double bond. When we're drawing out fatty acids, and it's easy to draw in that nice zigzag paper or zigzag pattern, we're going to just by default draw trans if we have a double bond. And so that means that if we have a cis double bond, we're going to have to pay attention to what we're doing, and we're going to have to do a little bit of erasing and fixing that double bond. So I am going to attempt to delicately, I was afraid that that would happen. I cannot just erase a little bit of my double bond. Maybe I can do it like this. Oh yeah, that's going to work. So I'm going to attempt to redraw this molecule a little bit. And it might not look very pretty, but I don't really care if it looks good. I just want it to have all of the right atoms in the right spot. So what I'm doing is just kind of twisting and moving carbon 10 up to this higher position. And I am also going to expand this existing bond from 8 to 9. I'm going to expand that up. And so that means that I'm going to move carbon number 9 is now located up here. And I'm going to reconnect 9 and 10. Don't forget they have a double bond. So even though this looks pretty gross, and I'm going to try to straighten this out as much as I can. This looks pretty disgusting, but I have got all 16 carbons. I have my double bond going in between carbons 9 and 10, which is exactly where I want it. And I have now drawn it in a cis conformation or configuration, so it's consistent with what the problem is asking me to draw. Let's see if my next one looks better. Next one, we're going to draw stearic acid, which is 18 carbons saturated. So we've got 18 carbon atoms. Saturated means that it is all single bonds. So all carbon-carbon single bonds. So this is going to be way easier to draw. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And if we want to number them, just to make sure we have them all, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. They're all there. So that one was nice and easy to draw. The last one that we are going to draw is transoleic. Transoleic. 18 carbons, mono unsaturated, so that means one carbon-carbon double bond, one of them. Double bond located at carbon number 9, and they didn't say omega anywhere, so this is not omega 9. This is carbon number 9 when we're counting from the beginning. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbon atoms. And let's number them 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's stop here and give our molecule its double bond. The double bond starts at 9 and goes to 10. 11, 12, 13, 14, 15, 16, 17, 18, they're all there. We are supposed to draw the trans configuration, and when we look at the double bond, we see that it is trans, so it's already in the right shape, so that's beautiful, that's perfect. The last question asks, saturated fatty acids, which here is an example of a saturated fatty acid, this guy right here. Saturated fatty acids and trans unsaturated fatty acids, which is this one, they tend to have similar physical properties. So this would have to do with, is it a solid or a liquid at room temperature, stuff like that. And those physical properties of the trans and the saturated fatty acids are different from the physical properties of our cis fatty acids. And so then it gives you some examples about whether or not they're solids at room temperature. Analyze the structures that you drew and see if you can come up with an explanation. And so if we were in class, we'd take some time for you to talk about it with people that were sitting near you. But since we don't have that luxury, we're just going to do this together. So I'm going to draw kind of a loop. This is the general shape of a trans-saturated fatty acid. Whether it would be mono or polyunsaturated, it's going to have that shape. And this is the general shape of our saturated fatty acid. The way that I'm drawing them, they kind of look like hot dogs. And our cis fatty acid has in the carbon chain this bump to it, like that. So because of that forced shape of the cis double bond, it's not a smooth, perfectly linear shape. So if we were to draw like kind of a cartoony representation, saturated fatty acids kind of have this shape to them, and trans unsaturated fatty acids kind of have this shape to them. But cis kind of have not straight, kind of a kinked up and uneven shape to them. And because the shape of the saturated and trans unsaturated, because their shape is similar, they have similar physical properties. And if you're feeling like you've heard this kind of stuff before and talking about nutrition and talking about fats and oils that are saturated and unsaturated, this is really all the same type of stuff. So one of the things that we know with these saturated and the trans unsaturated is when these molecules get together, like in a container or in your body, they can sit together really tightly like this. They can kind of form this nice little pattern. And because they can pack together tightly like this, they can be solids more easily. And they can also clog your arteries up more easily. So this is the saturated and the trans unsaturated. Whereas the cis unsaturated, because they don't have that linear shape, they do have a harder time packing themselves together. There is a way for them to pack together, but it's just harder for them to find that configuration. And because they can't pack themselves together all nice and orderly, like these guys can, these tend to be liquids at room temperature. And also, they tend to not be clogging up the insides of our bodies. So this is the cis ones.